Welcome to Topic 5, Unit 2, the complex plane DeMoivre's theorem. So recall from the Desmos investigation that we can plot complex numbers on the complex plane. We do this by having the real axis and by also having the imaginary axis. And our point is z equals x plus yi. Example 1, we're going to plot z equals square root of 3 minus I in the complex plane. So I'm going to start by drawing my complex plane, my real axis and my imaginary axis. I'm going to go positive square root of 3 on the real number line, and then I'm going to go negative 1 in the I direction. And so my point right here is z equals the square root of 3 minus I. So z equals x plus yi is a complex number in rectangular form. We refer to the distance this point has from the origin as the magnitude or modulus of z. We use the symbol absolute value, so sometimes people call it the absolute value of z, but really it's the magnitude, and it actually is exactly the same way we were calculating r when we were using polar coordinates, which leads us to polar form of a complex number. So we already know that z equals x plus yi is a complex number in rectangular form. If we substitute in r cosine theta for x and r sine theta for y, we get polar form, which is r times the cosine of theta plus I sine of theta. Keep in mind that in the polar form of a complex number, r has got to be positive and theta has to be between 0 and 2 pi. Also, this is kind of a lot to write out, so an acceptable shorthand for r cosine theta plus I sine theta is to say r cis theta, where c is for cosine, I is for I, and s is for sine. So example 2, we're going to write z equals square root of 3 minus I in polar form. Now when you go from rectangular form to polar form, you have to go through the same steps that we went through when we were working with polar coordinates. So we start with the sketch. So recall that we actually sketched this already when we were doing example 1. And so this is equal to the square root of 3. This is equal to negative 1. Here is our point z equals the square root of 3 minus I. So we are in quadrant 4. We can calculate the r by using Pythagorean theorem. So that's going to be the square root of 3 squared plus negative 1 squared, which is the square root of 3 plus 1, or the square root of 4, which is equal to 2. We can find theta by doing the inverse tangent of y over x, or negative 1 over the square root of 3. And this is going to give us the angle negative pi over 6. But remember the constraint that theta has got to be between 0 and 2 pi. So I need to add 2 pi to get a coterminal angle that is between 0 and 2 pi. So I'm going to add 2 pi, which is 12 pi over 6, and I get that theta is equal to 11 pi over 6. So we can say that z is equal to r, which is 2, cis theta, which is 11 pi over 6. Example 3, plot z equals 2 cosine 30 plus I sine 30 in the complex plane and write z in rectangular form. All right, so here's my real axis, here's my imaginary axis. I'm going to draw the terminal side of 30 degrees, which is about here. And then I'm going to mark my radius as equal to 2. And so this is z equals 2 cis 30 degrees. And now we want to write this in rectangular form. So I'm literally going to substitute in cosine 30 and sine of 30. So z is equal to 2 times the cosine of 30, which is equal to the square root of 3 over 2, plus I times the sine of 30, which is 1/2. I'll distribute the 2, and I get the square root of 3 plus I. Now we're going to talk about products and quotients of complex numbers. We saw this in the investigation as well, and you may recall that if I have two complex numbers in polar form and I want to multiply them, I just multiply the two radii together and I add the thetas. And if I want to divide two complex numbers in polar form, I'm just going to divide the radii and I'm going to subtract the thetas. Example 4, if z equals 3 cis 20 and w equals 5 cis 100, part A, we're going to find z times w. So this is going to be equal to my two r's multiplied together, 3 times 5, and then I'm going to add my thetas together, 20 degrees plus 100 degrees, and I get 15 cis 120 degrees. Part B, we're going to find z divided by w, which means I'm going to divide my radii and I'm going to subtract my angles. So I have 3/5 cis negative 80 degrees. Now I hope you notice that we have a problem here. Theta has got to be between 0 and 360 if I'm writing a complex number in polar form. So I'm going to have to add 360 degrees to negative 80, so I get a coterminal angle that is between 0 and 360. So negative 80 plus 360 is equal to 280. So my final answer is 3/5 cis 280 degrees. So now we've reached DeMoivre's theorem, which is a really elegant way to be able to raise a complex number in polar form to a power. And so DeMoivre's theorem says that if z equals r cis theta, then if we want to raise it to a power, we're going to raise the r to the power and we're going to multiply theta by the n. So example 5, they want us to write 2 cis 20 cubed in standard form a plus bi. So basically they want us to use DeMoivre's theorem to raise it to the third power, and then we're going to convert it into rectangular form. So this is going to be the same as 2 cubed cis 3 times 20 degrees. 2 cubed is 8. And 3 times 20 is 60 degrees. So now I'm going to write this in long form. This is times the cosine of 60 degrees plus I sine 60 degrees. I'll substitute in the cosine of 60 degrees, which is 1/2, and the sine of 60 degrees, which is the square root of 3/2. And I'm going to distribute, and I get 4 plus 4 times the square root of 3i. So that was relatively easy because we started in polar form. If we're given a complex number in rectangular form and we want to use DeMoivre's theorem, then we have to convert it to polar form first. So I'm just going to write 1, convert to polar form. And you have to remember that if you're going to convert to polar form, we have to start with a sketch. So this means I'm going to go out 1 unit on the real axis and 1 unit on the positive imaginary axis. And there's my point. My theta is equal to the inverse tangent of 1/1, which is going to be 45 degrees. I'm using degrees because it's a lot easier to use DeMoivre's theorem in degrees than in radians. And my r is equal to the square root of 1 squared plus 1 squared, which is going to be equal to the square root of 2. So I'm actually trying to find square root of 2 cis 45 degrees raised to the 5th power. So that means I'm going to take the square root of 2 and raise it to the 5th power, and then I'm going to take my 45 degrees and I'm going to multiply it times 5. Well, the square root of 2 to the 5th power is actually 2 to the 5/2, or 4 times the square root of 2, and 45 times 5 is 225 degrees. Now it'd be nice if we could say we were done, but they said put your answer in a plus bi form. So now I'm going to say this is equal to 4 times the square root of 2 times the cosine of 225 plus I sine 225. I will substitute in the cosine and sine of 225. The cosine is negative root 2/2. The sine is also negative root 2/2. So if I distribute the 4 root 2, I wind up with negative 4 minus 4i. So now we have reached the most complex of the complex numbers that we're going to be working with today, and this is finding complex roots. And this formula is very complicated, and I'm going to leave it here for you to be able to see. But the bottom line is that it's just easier for me to show you how this works. So example 7, we're going to find the complex cube roots of negative 1 plus root 3i. Now if you look at the formula above, you have to be in polar form. So let's go ahead and we will write this in polar form. So we're going to sketch a graph. Here's my real axis, there's my imaginary. I'm going to go negative 1 on the real, and I'm going to go positive root 3 on the imaginary. So my angle is in quadrant 2. My r is going to be equal to the square root of negative 1 squared plus the square root of 3 squared, which is equal to the square root of 4, which equals 2. My theta is going to be the inverse tangent of y over x, or the square root of 3 over negative 1, which is going to be the inverse tangent of negative root 3, which is going to give me negative pi over 3. That's in the wrong quadrant. I know from my sketch that I need to be in quadrant 2, so I'm going to add pi, or 3 pi over 3, and I'm going to get that my angle is 2 pi over 3, and I've already forgotten that I told you that it is way easier to use DeMoivre's theorem if we're in degrees. So 2 pi over 3 is the same as 120 degrees. So since we're looking for the complex cube roots, there should be 3 cube roots. So our first root we're going to call z sub 0, and what we're going to do is we're going to take our r, which is 2, and we're going to find the cube root of 2. And then we're going to take our theta, and because we're looking for cube roots, we're going to divide it by 3. So our first complex root is the cube root of 2 cis 120 divided by 3, which is 40 degrees. Our second cube root is also going to be the cube root of 2, but now I am going to take the 40-degree angle that I just found, and keep in mind that the complex roots, if you graph them, are equally spaced around a circle. So 40 degrees is about here, and if it's equally spaced, I have to take 360 degrees and divide it by 3, and that means that each one of these terminal sides angles are going to be separated by 120 degrees. So the second cube root I'm going to find by adding 120 to 40, and now I've got the cube root of 2 cis 160, and 160 is about over there. And my last cube root, z sub 2, is going to be the cube root of 2 cis, now I'm going to take the angle I just calculated, 160, and then I'm going to add another 120 to it, and I'm going to get the cube root of 2 cis, and 160 plus 120 is 280 degrees, and 280 degrees is about down there. So see how each of these answers are separated by 120 degrees. If we were finding fourth roots, we would have started by taking our original angle and dividing it by 4. Then we would have taken 360 and divided it by 4, and we would have been adding 90 to get our 4 answers. But we were finding cube roots, and here are 3 answers right here. That's all for now. Thanks for watching.